Got some good stuff coming out. Okay, so, oh my gosh. For Venn diagrams, what you want to do in general is you always want to, so for Venn diagrams, always start with the value with the most overlap and then just kind of bloom out from there, because otherwise you're going to double count stuff, which you don't want to do, right? So for Venn diagrams, always start with the area with the most overlap. Right, so our two kind of examples are like, and I'll just do A and B for now. A and B. So for example, that would be this area here. Or if you have three things, which we max out at, you can do Venn diagrams for more than 3 events. But we're not going to, it gets crazy. But then it would be this area here. And then I think of it as kind of blooming out. So then I'll say bloom out. So for example, that would be this area and this area, or this area and this area. Okay, making sure that you subtract the overlap. Bloom out. Making sure you subtract the overlap. And then same thing for the three event situation, then, or 3 outcomes, then you would have to subtract all of these overlapping areas before you could go ahead. So then what we get here is, let's do this example. So a survey of 88 OC students was conducted, and it was found that 24 people carried a tablet, 29 people carried a laptop, and 10 people carried both a tablet and a laptop. Okay, so we're going to start. So for this example, we're going to start by drawing our Venn diagram. You don't have to draw the Venn diagram, but it makes it easier, I think. Right? You could say that I know, let's see if I can find a different color here. This says that tablet and laptop has a count of 10. The tablet has a count of 24 and laptop has a count of 29. And N is 88. So we're going to have, oopsies, a tablet and a laptop. And what we're going to do, we're going to start here with the most overlap, in this case is 10. Now, because the question is asking how many people, we don't have to convert that to percentages, right? Or probabilities, although we could, right? 10 out of 88, but it's asking for the count. So then we just need the count. So here we have a count of 10 in the overlap. which means that if 10 had both, then 24 minus 10 have only a tablet, right? So that puts us at 14, and then same thing for the laptop. Puts me at 19. So what I'm doing is I'm doing just these half moon areas with the area subtracted. And then I have a total of 88. So n equals 88, which means that the total areas inside the sample space have to add to 88. So what I do is I can take away 14 and 10 and 19 from 88 and see what I'm left with. 45. So then here, let's see here. 45, you said? Nice. So 45 students have neither a laptop nor a tablet, right, out of those 88. So now we can answer how many people carried a tablet or a laptop. One thing to remember is that the or is either a tablet or a laptop or both. Okay, and so that's going to be 14 plus 10 plus 19, which was what? 14 plus 10 plus 19, 43. So here I'll say 14 plus 10 plus 19 is 43. Or you could do 88 minus 45 if you already found that 45. Right? So how many people carried neither a tablet nor a laptop? We already found that, and that's 45, right? Or we could say 88 minus 43 is 45, because that's what you did already. How many people carried a tablet only? Looking at our diagram, right, we see that it's 14. And how many people carried a laptop but not a tablet? That's going to be the 19. So kind of tricky when the only one that's really tricky is the or one, right? Because it has to be the tablet or the laptop or both, which people forget about. Yep. Is it from the quiz or the assignment? Because I can pull it up here if you're okay with that. Got it. Let's see here. Defining probability. I'll pull mine up and you'll tell me if it's the same. Oh, this one? The 3 Venn diagram one?
Just like numbers different, that's okay. So let's talk about this question.
You bet. Oh, let me just try to take a screenshot here. Done. And did you see there's a video?
Yeah.
I haven't checked them all out, but I think it's kind of fun that they exist. Yeah. Let's see here. It's probably good enough. Okay. So this is a 3 event one. Okay. And so a survey asks buyers whether color, size, or brand influence their choice of cell phone. The results are some numbers said size, some numbers said brand, some numbers said color, And these numbers are all going to be different, but how you solve it is always going to be the same. So we have 3 things, right? So 3 events or outcomes, which means that we have to draw our Venn diagram as, bless you, 3 things. So I'm going to denote them by size, brand, and color. And then following the same methodology, if we read through these, right, we're going to start here with 58 said all 3. So that means that, and I'm going to try to write it here, 58. So we start in the very, very center, and now we've got 58, right? And so that one's taken care of. Then we're going to look at 92 said color and brand. So color and brand is going to be, let's see if I can highlight this. This overlap, right? Where it's both color and brand, but we've already accounted for 58 of those. So 92 minus 58 is 34. And maybe I'll make a little note here. 92 minus 58 is 34. I'll only do that for that one, but I think you get the idea. So then if I pick a different color here, 99 said color and size. So then when I'm looking at this overlap here, I get 99 minus 58 puts me at 41. And then 147 said size and brand. Guess I should have picked a color that looks different from pink, but whatever. 147 minus 58 is 89. Then I can go and I can do the color. So now I'm going to subtract all the areas from the color circle that I've already accounted for. So in total, in the color circle, you're going to have the 229, but you've already accounted for 41 and 58 and 34 of those. So 229 minus 41 minus 58 minus 34 is 96. What's a color I haven't used yet? How about teal or aqua or whatever you want to call it? 96. So here, just as this example, I have 229 minus 41 minus 58 minus 34 is 96. Same thing for just the brand one. Let's see here. Light purple, maybe. Gonna run out of colors. 259 minus 89 helps if I type it in right. Minus 58 minus 34, 78. And about this kind of burnt orange. Same thing, 214 said size. So 214 minus 41, not plus 58, minus 58 minus 89 puts me at 26. And then finally, let's see here. Let's do, what's a color I rarely use? This blue I never use. 23. Oh, it's lagging, but I put it in the sample space. So inside the rectangle, but outside of all those circles, because they probably said other or something else. So none of those. Okay. So now, how many buyers were influenced by color and size, but not brand? Right. So I've got the color and size. That's the overlap of 41 and 58. But the 58 were also influenced by brand. So the number that we're interested in here is the 41. Mm-hmm.
So why are we not adding these three up, like 26, 41, 96? Because there were like 96 of those, they were like, influenced by only size. I mean, you know what I mean? It says not the brand. Are we just like excluding brand and not?
It's because it says and. So if it said or, then you would add them up, right? And take away all the areas that have the brand. But because it says color and size, the only time that that happens is here in this overlap. Make sure it's catching up here. So it's really laggy today, but so that's in this overlap. But then if they can't be in the brand, then we can just read the value, which is 41. And I'll use the same color. Yeah, so when it's or, then you would consider all the areas that satisfy that, right? But when we say and, then it has to be both. And then how many buyers were not influenced by color? So that's everything that's not color. And if we just kind of go back to, I guess we don't have the overall sample size, but what we could do is we could add up all the areas that are not color, right? There's lots of ways that we could solve this, but that's probably kind of my easiest solution. Tedious, but it's probably the easiest. So then I would say 26 plus 89 plus 78 plus 23, because those are all the areas that are not color. 26 plus 89 plus 78 plus 23 is 216. Oh, I guess I should have read all the parts, save myself some work, because what should I have done? I should have added up all of the areas, and then I would have the answer for the last question. And then I could have subtracted the 229 from all of them to get the 216, right? Or we can say 216 plus 229 has to be the total number, right? So 216 plus 229 is 445, which you can double check, right, that it's 445 by adding up all these areas, right? So just to make sure, I've got 216 plus 41 plus 58 plus 34 plus 96 is indeed 445. It should include the 23 because it's the total number of people surveyed. And I had the 23 here in the 216. I just started at 216. Yeah. I see. I see. I'm like, did I forget something? Did I forget to do something? Good. Yeah, so once you kind of start to see the pattern, it's like, okay, you start in the middle, and then if you've already written that number down, you can't rewrite it. You have to take it away before you can write down the new number. So you kind of chip away, but the key is to start in the middle and then kind of bloom out. And then you'll be able to answer all the colors, all the questions, and just remember that and has to be the overlap. Okay, let's see here. Chapter 4, I think it's chapter 4, which is just as a note, if you see kind of chapter 3, now chapter 4, it's because it used to be chapter 3. So they changed all the chapter numbers, of course. And then, but the material is all the same. So that's why it got confusing, but old chapter 3, right? If it's kind of from previous materials, here, we're gonna start talking about some distributions. We're gonna focus on the normal distribution. And then later we're going to move into the binomial distribution, which is kind of another distribution that we can look at. But we're going to focus on the normal distribution because it's what we're going to use for the rest of the term. Okay, so really important to kind of have a good handle on it. And let's do a little recap. A recap of last day. Not truly review. Okay, so if we have a normal distribution, right, it looks like this. It's symmetric, it's unimodal, and it has this kind of nice tapered down shape. Nothing is going to be exactly normal, but a lot of things are approximately normal. And that's why the normal distribution kind of came about, because it happens naturally in a lot of things: heights, weights, speeds. A lot of these numerical variables that we talk about follow a normal distribution. The only time where you're not going to have a normal distribution is when you're talking about money, usually, or if there's kind of if things start at 0. So money starts at 0, right? Or I guess you could have negative values, but that sucks. But in theory, money starts at 0, and then you increase. And most people, if we're talking about incomes, for example, then we have this kind of skewed to the right distribution, because there's only very few people who make a lot of money. Most of us are, down here. And so but the normal distribution happens naturally for a lot of numerical values. So we can describe a normal distribution by talking about, so here, this is the normal distribution. And we can describe it fully by talking about the center and the spread. Right, so where is this thing centered? Oh, it caught me off guard when it wasn't drawing there. It's better. So the center, and then I'm going to show it like this as the spread. It's not really how we measure the spread. The numerical measure of spread is the standard deviation typically. But we have the center, and for a lot of these things, we're just interested in where are the most common values found roughly. So if you're just describing a distribution, so if you get a histogram, which is how we're going to visualize distributions from data, sorry. then you're going to look, and if you have a normal distribution, then you're going to use the center, right, as kind of a jumping off point. This is where most values are, and you're just going to eyeball it. Right? The numerical measure of center the numerical measure of center for a normal distribution is the mean, which we've already talked about. Whereas if you have a non-normal distribution, which we're not going to talk about anymore today, but then you should use the median as a more accurate measure of center, right? And so the numerical measure of center is the mean, right? And so we know how to find the mean, and that's where this line is going to be, right? And then we can talk about the spread, the numerical measure of spread for a normal distribution is the standard deviation or the variance. Yes.
I'm just thinking, does the population has the normal distribution? Or is it
So it depends on the population of what. So most populations have a normal distribution. And so when we take a sample from that population, then if we see something that's approximately normal, then we can assume that the population is also normal. Sorry, this caught my eye. Oh. Okay, it's not the drywaller. I have to keep an eye on my phone and I completely forgot.
So I was actually thinking of a graph that we just did in environmental science class.
Okay.
It was like the population from 1800s to 2025.
Oh.
It was like after that industrial thing, the population goes like this, and after that industrial, it just went like that.
So then you'd have a scatter plot, right? Where, you know, your population over time is that what you mean? Did it look like that?
Yeah, like when we like do the histograms and stuff,
Mm-hmm.
we'll say like it's skewed to the left.
So for this one, because we're looking at two different variables, we could make a histogram of the populations. And in this case, what would it look like? It would probably follow a normal distribution, because there's very few times where we have kind of this low population, and then there's very few times where you have this high population, but I don't actually know. I don't know of an easy way to translate a graph like this, a scatter plot like this, into a histogram for just the population, right? So histograms are only for, we put them like this, but it's only for one variable. And then we have the frequency on the, sorry, that looks weird. So how many times was the population between this size and this size, right? And there would be some count. How many times was the population between, or how many years maybe was the population between this size? So we would have these bins.
Like
right?
in Excel, it does make like all sort of graphs. Is there a time where we can say like for this data, we can't make this particular kind of graph.
Uh,
I'm just assuming, like, is there like
mhm.
some, like, situations where we say, no, I can't plot it in histogram, I can't plot it in like Biol.
As long as you have a numerical variable, you can make a histogram. And that's usually how we visualize a numerical variable, is with a histogram, but it has to be numerical, right? So this has to be a numerical variable in order to make a histogram. Whereas here, right, this scatter plot is actually a special case because time is on the x-axis. So we call that a time series, but I'll say that again later. But that's about as far as we go into time series, because the tricky thing about time series is that the population for this year depends on the population from last year, right? So you have to take that into account when you're doing your analyses. And so it gets a little bit tricky and kind of beyond the scope of this course. But usually what people end up doing is they ignore that and they just say, oh, okay, well, I see this trend and I'm happy with that, right? But if you've got time on the x-axis, this is what we call a time series. So it's a little bit special. But yeah, so histograms are only for one variable, whereas here, if you look at the population on the y-axis and the time on the x-axis, then you've got two variables, right? Population and time. So then here, this is one variable, which is population, and this is two variables. Population and time. Nice. Okay. So if we have measurements from a normal distribution, right? And usually the question will say, these things follow a normal distribution. And so grades, for example, tend to follow a normal distribution. And one really common example that we use is in the States, they have the SATs and the ACTs. And so they're on different scales. So I think the SATs are, you can get scores in the hundreds or thousands. I don't really know. I'm not in the States, so I don't know. But you can get kind of these high scores because it's out of a lot. And then the ACTs, I think it's more normal to have scores in the 30s, the 40s, that kind of thing, because it's out of fewer marks, right? But how do you compare these values? What you would do is you would take into account the mean, right? So the average score as well as the standard deviation, and see how many standard deviations from the mean are you, right? And so that's what gives us the standardized scores. So to compare measurements from two different distributions, we usually standardize the measurements. So we usually standardize the measurements. The standardized value is what we call a Z-score. The standardized value is called a Z-score. So Z is X minus mu over sigma. And once you see the video, we kind of do more examples of this, but I think we can kind of jump out from here and still have a pretty good handle on things. And so X is going to be the placeholder for the measurement. Mu is going to be the mean. And sigma is going to be the standard deviation, of course. The area under the curve is going to be a probability. And if there's lots of area under the curve, then there's a high probability of being in that region, right? And so here, if we go to our normal distribution, looks something like this. And I'll have the mean here, mu, and then I'll say just sigma down below because it's hard to kind of draw it anywhere. I did show it as the spread, but that's not quite true. We can fit 3 standard deviations on each of the curves. And in the video, I'll go on and on and on about how important it is to remember that these tails actually go to negative infinity and positive infinity. And so they never ever close on the axis. Okay. But the area under the curve here,
It can't be both positive.
no. So what happens is it gets kind of like mind-boggling, but when we draw a normal distribution, then we assume that those tails never ever close.
Oh, so it's just going on.
It just goes on and on and on. And if we think about the area under the curve as the probability, area under the curve is a probability. And if you've taken Calc 2, for example, then you know how to find areas under the curve. The problem is the function, the Gaussian distribution function, is very difficult to integrate, right? And so, but we would use integrals to find that area under the curve, right? And so all we need is to know that, okay, the area under the curve is a probability. So then I can use this area and I can find probabilities. And that's pretty cool, right? So here, if I have lots of area under the curve, then the probability is high, right? That those values would fall somewhere in this range around the mean, which makes sense, right? If we're talking about heights, there's probably very few people who are exactly the average height of women, let's say, right? But most people are hovering around the average, right? So there's very, very few people who are exactly the average height. That would be weird. But then most of us are hovering around the average. And then there's some really tall people, and then there's some really short people, but we have this kind of distribution. Gets confusing, I think, to talk about heights, because then I imagine people standing next to each other, and that's not really what's happening, right? But you're kind of laying on top of each other, I guess, to make the bars in the histogram. Kind of weird. Okay, so one key thing to remember for probabilities, if the area under the curve is a probability, then the total area under the curve must be 1, right? Probabilities go between 0 and 1. And so, so the total area, therefore the total area must be 1. Yes, that's always true. Okay. So instead of integrating this function over and over and over again, which is technically what we would be doing, right? If I want to find the probability, so for example, find the probability And I'm going to do kind of a fake example here because I know I need to introduce a little bit more. But for example, of being between here and here. Like this. So I've got x1 and x2. Just using x's, you can use a and b or whatever, right? But I'll use x1 and x2. And the only reason I'm using x's is to match up with this formula here. So x is the measurement that we're interested in. So if I'm interested in the probability of being between x1 and x2, so for example, being between 150 centimeters and 170 centimeters, for example, right? Or whatever, then what would I technically need to do? I would need to integrate this function. And I think I've asked you guys, have you guys both taken Calc 2? No. Uh-oh. I just assumed.
I have.
You have?
Mm-hmm.
Okay. Then don't worry too much. We're not going to integrate anything, but it is what we would do. So then we would take the function of this, which is a kind of an elaborate function of this curve, and then we would integrate between x1 and x2 to find that area. Now, we don't want to do that, and we don't have to. And that's where the Z table comes in. So the Z table gives us areas under the curve. But notice how it would depend on what the mean is and what the standard deviation is. So what we have to do is we have to standardize these scores first, and then we can use the standard normal table. Okay.
What do you mean when we say standardizing things?
It means converting it to this Z. So a Z is a special case. So the Z distribution, so here, I'll finish this thought. Instead of integrating the function between x1 and x2, I'm just we can use the standard normal table, which I'll just call a Z table. And I brought some printouts, so you'll have it in your bundle tomorrow, Sarah. Okay. So the standard normal distribution is a special case. So the Z distribution, if you prefer, it is a normal distribution. So all we're doing is we're taking what was originally a normal distribution, and then we kind of shrink it down to this standard normal distribution. And so it has the same shape. Okay. It has a mean. So Z always has a mean of 0. If we think about a measurement that is exactly the mean of that group, then the standardized value would be 0. It's 0 standard deviations away from the mean, right? Because it is the mean. And sigma, no, it does not. And sigma is 1. Okay, and so the notation that we use is we say that Z follows a normal distribution with a mean of 0 and a standard deviation of 1. So I'll write out how you read this. Z follows a normal distribution with a mean of 0 and standard deviation of 1. So then what we can do is we can always take something that follows a normal distribution and we can standardize all those values. And then the Z score that we find is how many standard deviations away from the mean a measurement is. Okay. So the Z score which as a reminder, Z is X minus mu over sigma, right? Where X is the measurement. And I'm not going to define mu and sigma. I think we're all on board. So the Z score is the number of standard deviations a measurement is from the mean. And here so the number of standard deviations, which is sigma, and then the measurement, how far X is from the mean, mu. Just to kind of link those up. But that's going to be really important to remember that the Z score is how many standard deviations away from the mean are we? Okay. And there's different things that we can do. We can approximate the area under the curve by using what we call the 68, 95, 99.7 rule, which breaks it up into intervals of 3, because as a guideline, before these, we can only fit 3 standard deviations on either side before the curve gets so small. Remember, it never closes, but before it gets so small that we really don't care about that area, it's going to be less than 0.0002. So then we stop caring. Yeah.
I have one question, like where we consider the numbers on that thing, where we say like it goes to negative, where we consider like, 0 in the middle.
Yeah. So for the Z distribution, if we've standardized it, it'll always be centered on 0. And then it would go to, so here, this goes, so the Z distribution goes to negative infinity and positive infinity. That doesn't look like infinity, but close enough. And that's only true for the Z distribution. Okay. So to find the areas under the curve, because that's going to be our ultimate goal, we need to first standardize the values so that we can use that table that I gave you, because the table gives us the values that we need. Now, let me see if I have, it's probably here. Okay. Oh. Bring it in here, I think. And I'll erase this all. Okay, so the table that I gave a printout out of looks like this. Now, it looks scary in the beginning, but what's going on here is And I do explain it better in the video, or I hope better in the video. We'll see. You guys let me know. We've got the Z score. So we're going to have Z values, and it stops at some point, but the area keeps going. But we've got Z scores that are increasing in the left-hand margin. And then we have so the whole number and the first decimal is in the left-hand margin. And then we can join it up with a second decimal place in the top margin. So these areas under the curve, or sorry, I gave it away. These table entries, so notice I'm going to use, and I see that it's totally lagging here. Ha, okay. Sorry, Sarah, we're back. It disconnected me, booted me out. Is it just, I'm sharing my screen. Okay. I guess we're back on track. I don't know. Can't see if my okay. All right.
I can see everything.
Awesome. Sorry, it totally booted me out and I'm so lost. Anyways, it seems like it's still recording. So, all right, cool. Okay. So I'm going to be calling these table entries, and the table entries are going to be these values in the table. Okay. And so I'm going to kind of screenshot a section here or portion. Just so we use the same terminology. So here, when it says table entry up here, I'm going to use that terminology for these values, or I'm going to try to use the same terminology. Okay. So what this table does is it's broken up at each Z score. Remember, Z is a normal distribution centered on 0 with a standard deviation of 1. So then we can have the Z scores and we can look at the Z scores like this, because we also know how to convert a measurement to a Z score using that formula. So if Z is centered on 0, then at some point here, if we start at the smallest value of Z that's given in the table, then we would have -3.49. Okay, so that would start somewhere out here, negative 3.49. Now what it's saying here, the table entry for Z is the area under, sorry, that's really small. Table entry for Z is the area under the standard normal curve to the left of Z. So what it's saying is that, okay, if I feed it a Z of negative 3.49, the area to the left is going to be 0.0002. So then here, how I show that is that this area must be 0.000, I'm missing a 002.
There is the unit for that area.
No, the area is just a probability which has no units.
Okay,
It is very confusing.
it's not that area, it's just. When
It's-
we say area, we say like probability.
Yes. Yeah. So the area under the curve is not an area like we think it is. Like it's not, you know, A times B or something like that. It's the area under the curve is a probability. So what that means is the probability of having a standardized value less than negative 3.49 is 0.0002. So I'm going to translate that here because I think that'll be good. So this means that the probability of a Z score less than, because then, so here on this, this axis, this kind of x-axis, we're going to have our Z scores, right? So Z goes from negative infinity out to positive infinity. So you can absolutely have Z scores that are beyond negative 3.49, and then it's going to be symmetric. So on the positive side, we'll max out at 3.49. But the only thing that's happening is, okay, then the area gets so small that we say it's just approximately 0 in those tails. Approximately. It's very important that we just say approximately, because it's not 0. There is some probability of it happening, right? There is a probability of winning the lottery, for example. It's just very, very, very small. Right? And so here I'll finish kind of writing about this one. So the probability of a Z score less than negative 3.49 is 0.0002. So the thing to keep in mind about the table is that it's always going to be the area to the left. What if I wanted to know, okay, so if I know that the area or the probability of being less than negative 3.49 is 0.0002, then what's the probability of being greater than negative 3.49? Awesome. Right, so then to find the probability above, we leverage the fact that the total area must be 1. So then we take 1 minus 0.0002. Which is 0.9998. The probability of a Z score greater than negative 3.49 is 0.9998.
So like we can't ever find like a probability to the right with the Z.
That's right. So the Z table that I'm giving you, and there are lots of different versions, so that's why I'm kind of saying, okay, the one that I'm giving you only gives it to the left. Yeah. But they all leverage the fact that it's symmetric. So sometimes it'll do weird stuff, like I've seen one where it gives the area between 0 and the 1 value on the one side. So there's lots of different weird ones, but the one that I'm giving you is the most common one. And of course, we would use software, right? We would use Excel, which has a built-in function. We would use R, we would use, you know, whatever software we're comfortable with. Okay, but Excel has a built-in function that just does it. Okay. So the table is definitely old school, but it's handy to have, because sometimes if you're working on a problem, and a lot of these problems that I'm giving you assume that you're working with the table, and so it should work with software too, but because they will be similar, but we're maxed out to 4 decimal places here, and that's kind of the problem. But so oh yeah, so the table is definitely old school, and I don't love using old school things, but this is the one that kind of makes it a little bit easier. Okay, so let's see here. I want to get to, and like I said, you'll have to watch the video if this doesn't make sense. I've got the steps to using the Z table, but if you wanted to use R to find the area under the curve, then you can do that. And it does just give you the area to the left as well. But I know I'm not going to have time to actually do the example that I wanted to do today, but that's okay. But I will have time to read it and kind of talk you guys through it. And then we can kind of jump in on, or maybe I'll give you guys the assignment of watching the example for Friday. How about that? So here's kind of a typical scenario. So a cereal manufacturer has a machine that fills the boxes. And I know I have printouts of this somewhere in my office, but I have to clean my office. I haven't cleaned it since I left before COVID. So I kind of got out of there in a hurry. So it's a complete disaster. I know I have printouts. I'll find them. Okay, so a cereal manufacturer has a machine that fills the boxes. Okay, boxes are labeled 16 ounces. Now, when you go to the store and you buy a box of cereal, and if it said 16 ounces, we all understand that it should be around 16 ounces, might be a little bit less, might be a little bit more. But if it's significantly less or significantly more, right, depending on which side, right, those happen infrequently, but they do happen, right? And so they would make up the kind of smaller areas on our normal distribution, but they do happen, right? And so a lot of these manufacturing processes are focused on making sure that you're filling these boxes so that they're not underweight, but not overweight either, because then you'd lose money and you don't want to, you know, overdo it. So if a machine is set at exactly 16 ounces, the normal model applies. Then about half the boxes will be underweight, right? Because if we set this machine to fill at 16, if the total area under the curve is 1, right, then the probability of being underweight, so underweight meaning less than 16 ounces, then that probability must be 0.5. Right? So what we want to do is, well, we don't want to have that many be underweight, right? Considered underweight. So usually what we do is we shift this, we tell it to fill at a different amount, and we're going to figure out what that amount is. So, oh yeah, and then it goes on and on and on, and making the consumers unhappy and exposing the company to bad publicity and possible lawsuits. Okay, we get it. To prevent underweight boxes, the manufacturer has to set the mean a little higher than 16 ounces, right? Because what does that do? Well, if we use the same fake scale here, 16, then if I take this curve, So here's 16. And if I take this curve and I shift it something like this to some other mean amount, right? Now, only this area is underweight, right? So that's why we shift it a little bit higher. And then we say, okay, well, yeah, these are less than what we told it to fill, but it's still more than 16. And then so any underweight boxes are less than 16. So, and there's a typo here, but that's okay. Don't charge extra for that. Based on their experience with the machine, the company believes the amount of cereal in the boxes fit a normal distribution. Okay, so that's why we're able to draw the curve with a standard deviation of 0.2 ounces. The manufacturer decides to set the machine to put an average of 16.3 ounces in each box. So what does our distribution look like? So from there, we know that, and I'm going to bump these over here. So then what we have is we have a normal distribution, because it says centered on 16.3. And then usually what I do is I just jot down the standard deviation somewhere on there. I'm ignoring units because the units will come up naturally, but usually I'm really bad because I just ignore units. And I know you guys are going to be so good with units, but I'm really bad with units and I get sloppy. And it's okay because you usually don't have to add the units on the assignments. Oh my gosh, I'm out of time. So just to kind of wrap up here, there are a series of questions here that I'll make you work through in the video, but I also gave some practice problems. It's called assignment 3, but it's definitely just for practice. And I'll post those solutions so that you have them for next week. All right. I'll stop this recording. See ya.
Thank you.